Find the values of x for which f of x is sin x is concave, and those for which it is convex. So here's a graph of sin x. We can see here it is convex, and here it's concave. Every time it meets the axis, there's an oblique point of inflection, and we know that this is a point at which the concavity changes, or the shape changes. So the graph is concave along this section, and then it reaches the oblique point of inflection and changes to convex. So f of x is sin x, the first derivative is cos x, the second derivative is negative sin x. If we look at the points of inflection, so where f double dashed x is equal to 0, that means, of course, that sin x is equal to 0. And we can see from the graph, or just know from our earlier work with trigonometry, that means that it's at integer multiples of pi. We could write this as x is equal to n pi, where n is an integer. We can see that the curve is concave for 0 to pi. So we can see that on the graph. And then it would be concave from 2 pi to 3 pi, and so on. So from even multiples of pi to odd multiples of pi, it's going to be concave. These are the points where the second derivative, of course, is negative. So it's concave for x between 2n pi and 2n plus 1 pi, where n is an integer. Just think about n being an integer, then 2n is positive, and 2n plus 1 is negative. So that's what we pointed out down here, that from even multiples of pi to odd multiples of pi, it's going to be concave. And so it's convex for 2n plus 1 pi to 2n pi, where n is an integer, again odd multiples of pi and even multiples. So from here to here, and from 1 pi to 2 pi, it's going to be convex. And so by using this notation, we've been able to specify all of the places where sin x is concave and all of the places where it's convex.